So hi everyone, my name's Yinzheng. I'm a PhD student of the University of Liverpool, and today I'll be presenting the process mining algorithm for Online Intrusion Detection System. So I will briefly go through these small sections. So first of all, I'll introduce a little bit about the process mining itself, and then I will describe how we apply the process mining on on the network packet data, and then how we develop our new algorithm to make the process mining in an online fashion, so it can detect the intrusion in an online way. And then I will show some comparison between other algorithms. So first of all, about the process mining. So usually we have two steps. The first one is process discovery. So basically what it does is we have an event log, and we then apply the mining algorithm on the event log, then generate some process models. Then the second step usually we'll do is to analyze the process model to determine if there's any anomaly or it's normal. So in our paper, we proposed a process mining inspired technique that is a pre-processing algorithm, and that can be applied to the network packet data, and then it outputs some the output can be applied with some classifiers, for example, the machine learning or outlier detectors. So here's an example of how process mining works. So we on the left side, we have 5 traces or cases in process mining. And in total, we have 7 different event classes. And the event classes basically is just from A to G, 7 event classes. And from these 5 traces, what we can get is the model on the right-hand side. This is mined from the fuzzy miner, but we haven't applied any abstraction with it. So we keep everything like as the initial model. What we can see here is we have some number on the nodes and some number on the edges as well. So the number on the node basically means how many times this event class happens, and the number on the node, the weight on the edge. The weight on the edge means how many transactions has happened. For example, this part from A to B, we can see the number on the edge is 3. So basically that means A to B has happened 3 times, as you can see in trace 1, 2, and 4. That's where it happens. So this is basically the frequency it happens. So here's a question. So how can we like apply the process mining on network traffic data, right? What we can do is, so with the first of all, we have to only keep the non-numerical values, the like events and transactions, because this is what the process mining handles. It's about processes, so we only keep non-numerical values. And the second step, we can define, because basically the network data, it is just a sequence of packets. So packet here in the notation we use P, so it's just a sequence of packets. And then also we know that some packets belong to some flows, because the network connections is basically network connections between the server and the client. So we will have multiple network flows. So each network flow is basically just one connection. So the flows can be converted into cases, and the set of the traces is basically the event log. It's equivalent to the event log, and we can have a log of the example. So here's the example. It is a fragment of the network data we connected. So as you can see in the yellow part, it's some basic information about the packets, for example, like the timestamp and the IPM ports. So we can use the information from the left-hand side, which is in the yellow part, to reconstruct the flows or the network connections. So and the green part, it's the attribute we kept for the process mining itself. So we only use the flags from the network header, like synchronize, acknowledge, something like this. So after we reconstructed the traces, we will just discard the yellow part. So after the reconstruction of the trace, what we get is this smaller table here. We only have the flags, as you can see, and the side. So the side basically means where the packet is sent from. If it's C, then it's coming from the client. If it's a server, then it comes from the server. We can simply like create this attribute by looking at the IP address and the port. So we have these information here, then that will be ready for us for the process mining. But the question is, how can we mine how can we do the process mining online? Because traditionally we can apply process mining on the network data, as I showed. The problem is usually the captured packet data is huge. It has a lot of data, and for the intrusion detection perspective, we are not expecting or expect to do the analyze after we connect a large quantity of data. What we have to do is do it online. For example, for each single packet we receive, we have to determine if there is an intrusion or not. So we have to make this process mining online. And what we did is we applied the sliding window. And so the sliding window will have a size L. And in our experiment, we used 500. As you can see on the right-hand side, there's a chart. And so we can mine a small model, relatively small model, with 500 packets, and we call this matrix A, because essentially the fuzzy model itself is just a graph, so it's just a symmetric, an adjacency matrix. So after that, we slide the window to the right-hand side, and we will mine another snapshot A. And we just repeat this until we reach the very last packet, which is PN, and then we will generate, if we can see on the next slide, so we can generate a series of snapshot A's. And in these A's, we have 26 event classes used. So during our experiment, we observed that there will be like around 23 possible headers in the network data, and plus 3 like other tokens, start, end, and others. So the others is basically default event class. If we observe something that's not included in this table, some rare cases, we will just classify it as others. We have these 24 event classes, 26 event classes. So the A should be like a 26 by 26 adjacency matrix, because it's a graph. So that would be like 26 by 26. And we used a state table like approach to keep the transition of last transition, because usually if we only consider 500 packets, it will be probably somewhere between the start of the connection and end of the connection. So 500 packets would not cover the whole network connection. That's why we have to keep the previous transition to prevent some information loss. And also this state table will give some performance boost, because in that case, we wouldn't need to mine the snapshot every single time we have a new packet coming. The only thing we have to do is we reduce 1 from the weight from the previous transition, and we add 1 for the incoming transition. So we only keep 1 like snapshot in the memory, and we just like manipulate it to create this series of adjacency matrices. And of course, for the training purpose, we have to label it. So from the IDS 2018, that's the dataset we used, that packet dataset, we have the label data, so we know which packet is from the attacker and which is not. So if we know that this packet is from the attacker, then we will just mark it like this. So we mark this matrix with some label like attack, and if there's any packet that is coming from the attacker, will mark this adjacency matrix as attack. And then what we do is just divide by 500, divide by L, which is our choice, to normalize the value. And here we go, some output from the series of adjacency matrices. So as we know, we have 26 by 26, so the adjacency matrix is 26 by 26. So we expect 676 possible relations or transitions. And here in this chart, I only selected like 20 of them. And what we can see is the attack for this one, left side, it start around at around 50,000 mark, this packet. And then what we can see is we can observe that once there's an attack happening, the fluctuation of the output of our algorithm start to stabilize. And that definitely says that we have observed something. On the right hand side, it's the same. It's very similar. So after that, we applied few number of different neural networks for classifier, for the binary classification. But you know, this table is just a comparison with another preprocessor. It's called CSV flow meter. It's another preprocessor that will generate some data, and then you can apply the the classifiers on it. So our preprocessor has it's not like every single different attack type has outperformed the CSV flow meter, but what we can see is it's the performance is still promising. This is for binary classification. We also did the anomaly-based intrusion detection setup. So we have used different outlier detectors like I showed in this picture. And we can clearly see that our preprocessor have outperformed the CSV flow meter for the anomaly-based setup. This is the receiver operating characteristic, ROC. So basically, a larger the area means better the performance. And so here's the conclusion. So basically, what we get from here is we get the promising performance, but the performance is not like completely outperform some other preprocessors. But the problem is it's depend on like how you compare things, right? And because we are doing online and like CSV flow meter, you have to wait for the connection to close, and then it will generate a output. But our preprocessor will generate output for each single packet, and that's the fundamental difference between our processor and the CSV flow meter. And then this is very extensible. So basically, by theory, this would not only work on network data. So anything that can be converted into event log, you can apply this algorithm, right? Like other type of things, and also you can apply any kind of classifier to the output of this algorithm. That's everything. Thank you, and like please, if you have questions.